I hope you are doing well in this course and you are with me with enthusiasm. Now, this is lecture 3A. We will give the main motive is to give the electrostatics of conductors, the basics. Much of it you are familiar in some form or the other, but we'll now sort of review such that we can take at one more level in the deeper in the next lecture. All right, so let's start off. Uh, why mobile electrons appear in some solids and not others? That is, we know, for example, metals or conductors are conductors because there are mobile electrons in them. Now, to give, so there is a free electron model of the metals that says that the valence electrons in some of these metals are responsible for the conduction of electricity. And that is why they are called conduction electrons. Okay. Um, so let me, for example, let me take an example. Let's say sodium. Sodium 11 has this as the core, and there is one valence electron 3s1. Now this 3s1 being the third is quite out and is not very strongly bound to the core, and hence is the valence electron. This is the electron that gives you the chemical properties. But when inside a solid, this can become almost free and become mobile. That's the kind of understanding that you would have gotten in school also. This valence electron, which occupies the third atomic cell, is the electron which is responsible for chemical properties of sodium. We know that. Okay. So let's say how many such electrons are there in, let's say, copper. Okay. So copper molecular weight is 63.5 grams. And so one molecular weight of copper will have Avogadro's number of electrons because each copper atom would have given one valence electron. Okay. And hence there'll be so much. And that'll approximately in 63.5 grams of copper, how much coulombs? 10 to the power 5 coulombs. Except that copper is indeed neutral because there are as many positive charges, a core of the atom which are positive charges. But there are so many mobile electrons. So this is the what I was saying, core electrons, and then there's the valence electron, loosely bound. That's a very rough high school idea of how does a metal form. Okay. But why are mobiles, if they're mobile, why are not the coming out of the metal? Of course, you know. Okay, you have studied that in school also. They have to surmount a work function potential to escape. They are inside the metal because all around there is a work function. Once they have enough energy out of the work function, then they can come out. All right. What is the typical work function? Electrons. Sorry Electrons would have to have in copper is about 4.48 electron volt. In aluminum, it's 4.2 electron volt. We use these values every day in the lab to make devices out of them. The work function is an important quantity while making devices. But what is a conductor in any way? But is there a perfect conductor by any chance? There isn't a perfect conductor, but I think metals come pretty close. So this is a good conductor of electricity. Normally, when it's a conductor, there could be a good conductor of heat, thermal conductors. Okay, but when we normally in this course we say good conductor or a conductor simply, it means an electrical conductor. Have you ever wondered, are all good electrical conductors also thermal conductors? Good thermal conductors? Of course not. Okay, stainless steel, for example, is a good electrical conductor, but is not as good thermal conductor. And diamond could be an extremely bad electrical conductor. In fact, it's an insulator and highly insulator, but it's an extremely good thermal conductor. Okay, of course, many metals are both good electrical conductors and thermal conductors. Now we know that resistance of is depends on. Suppose I have a tube, or is okay, and so this is, let's say, area A and length L, and then the resistance would be rho L by A, and we normally measure it in terms of ohm meter, okay, or more commonly in this area in terms of ohm centimeter, okay. It's just a uses ohm centimeter. So that's the resistivity of the material. Resistance is a particular piece, but resistivity is that of the material. For example, copper would have in normal circumstances resistivity, but a particular piece of copper of certain area and length would have resistance. This material property is also often expressed as conductivity. We have been using sigma as the surface charge density, but in the area of some metal studies or solid state, it is also called sigma. Okay, the conductivity. So sigma is the conductivity. 1 by rho is the conductivity. So it will be inverse of ohm meter. And a typical good metal, okay, silver or copper, has a room temperature resistivity in the order of micro ohm centimeter. It's good to know, okay. That is of the order of 10 to the power minus 6 ohm centimeter, or 10 to the power minus 8. So that is as good as a good conductor for our course, all right, for electrostatics. Now, why is there such a range of conductivity in nature? Let's see if in terms of ohm centimeter, okay, there is a huge scale in nature. 10 to the power minus 6, I just said, okay, uh, for good metals, right? And let's say that's for copper. And for glass, 10 is 10 to the minus 6, 16 orders of magnitude more, okay? Uh, 10 minus 6, glass and copper. And then you have fused quartz, okay? Then even it'll be 10 to the power 18, okay? But there is also superconductor. That is, I said perfect. This is a perfect conductor, but electrostatics of superconductor is very different from conductors. So we'll not consider that. Maybe later in the second half of the course, we'll do that. But let's consider broadly two divisions. Okay, one is conductors and insulators. They're also in between semiconductors. Semi meaning they're half conductors and half insulators. Okay, we'll refer to that sometime, but not in this course. Why are some conducting and others not? We know it's because of the mobile electrons. So, for example, diamond, okay, is 10 to the power 14. Okay, but silicon can be actually varied, and that's why you have electronics. That is not a conductor, not a insulator, and its conductivity can be varied for a wide range. In fact, by doping it, and that is why it gives rise to such technology. Uh, as I mentioned last time, the valence electron, which is almost loose, and in the solid form, these copper atoms, or say sodium atoms, they are pretty close by. And because of that, these valence electrons, while moving, can go to any of these, okay, can lose their way and can go to the next atom, next atom, and next atom, and so on. All right. So, and because of that, they can freely go anywhere in the metal's volume. And that is why we call them free electrons. They're sort of loosely moving around where the cores, where the atom is, that those ions are fixed. So these positive charges are fixed and these electrons are moving around. That's roughly the mental picture that you have of a metal. So as I said, 10, if you take it, so freely wander about 10 about 22 electrons per centimeter cube. But the conductor is neutral, okay, as I said. So what happens if you add extra charge to it? That's the question that we're going to consider. Obviously, the charge, and it tries to be neutral, and it sends it to the surface. And that question was actually worried a lot of people. For example, Benjamin Franklin was totally, he observed this, that when he puts something into a metal can, a cork, then it gets attracted outside but not inside, which means in a metal can, which at that time were called lead-in jars, okay, the all the charge was outside the metal, and he was mystified. He's in his letters, he writes to people, I've observed this but I just can't explain, okay. And it was indeed explained, okay, and it was invented and explained by Michael Faraday, his genius, to the extent is so much of his belief that he put to very high voltage and put himself inside a room which was a metal covering, okay, and he could trust the fact that he will not get electrocuted because all the charges would be outside, or it was grounded, and hence it will not matter, okay. And today this phenomena, which is called the Faraday cage, okay, gives you protection from the electromagnetic fields, is there everywhere in technology, in your microwave that you use in the kitchen, inside the airplane, because it's a metal body. If you go for MRI for some testing, that room has to be free of electromagnetic interference. So it is completely shielded by metal in all our labs. And today, in fact, we are working on something, a foil or something cloth, which is conductive, and you can put it in your purse so that the credit card information, thieves cannot take it out, okay, through some radio frequency or some electromagnetic waves. Okay, so it has many, many uses, and in the lab we use it every day to shield things from others, from from outside interference. Um, let's ask the question of our main motive is to electrostatics of conductors. Just to put it more dramatically, okay, that these conductors, as if they have a very simple but powerful constitution, okay, in which they say, we the conductors of the world solemnly resolve that we will not allow any net charge inside our body. So these conductors, once you have termed them as conductors, means they'll conduct. Any charge is there, they'll move because of the electrons are mobile. And with that, they can say that we will not allow any net charge inside our body and keep the inside of our body free of electric field in all circumstances. These are all consequences of the fact that there are mobile electrons, because if there is they are mobile, and if there is a field, so if there is indeed a conductor, okay, and there is some field here, and then of course the field will make the charges move, okay, till they go to the surface, such that inside there is neither charge nor field, okay. um, so once you are given the boon of conductivity to this material, it means that E is equal to 0 inside. Okay, because if there is E and there are electrons, they'll move. Okay, and so they'll take the charge away. So E is 0 is a direct consequence of the fact that you are saying that electrons are mobile or it can conduct electricity. So that is under electrostatics, okay, rho is equal to 0 and E is equal to 0 inside a conductor. So that's the operating definition of our conductor in this course. Okay. At the moment, we are not talking about uh, that the conduction of electricity. That's the next part. We'll worry about it, and that is why I had said that it is under electrostatics. Okay, so rho is equal to 0 and E is equal to 0 inside a conductor. So E is equal to 0 inside a conductor has important consequences. One you can see below. Okay, we'll go one by one. So all charges must go to the surface. There can be charges, but they cannot be inside the body. Why? Because once you have they move, finally where do they stop? They will stop at the surface. And the surface they cannot go because there is a work function. So all the charges that will move in such a way that they end up at the surface. And E is 0 inside, and rho, that is the charge density, is 0 inside. So the whole conductor, that's why since E is 0, okay, inside, there is no new, whatever is the potential, okay, is the potential throughout the equipotential surface and body, throughout the volume also. That is equipotential volume as well. Throughout so whatever is the potential, there could be potential because it's in the surface charge could be rearranging. That you could have given some charges, net charge also, it would have gone to the surface. So, but so it could be potential. But if you ground it, then the whole thing gets grounded, 0. Okay, so it's an equipotential. That's a consequence. The field at the surface is normal to the surface. Okay, and of course we know that E is minus grad V. Okay, and if it is an equipotential surface, then E is normal to the surface, to the equipotential lines or surfaces. And that is why your del V in the normal direction to the surface, at any point in the surface, it could be very irregular shaped, but everywhere the grad dot n or the del V by del n in the direction of the normal, the partial derivative of the potential, and that is, we can prove that. Um, so, sir, so, so let me, we can easily prove that. I'm sure you have seen that E, we just take the fact that E is equal to 0. And then now we can draw, suppose there is some sigma, okay? We can draw a small Gaussian surface, okay? And it's very close. And it will be normal to the surface, okay? So, and if there is some sigma here, at this place, there is some sigma here, okay, then all the contribution is a charge enclosed. So if I say area A, then in the Gaussian surface, then the charge enclosed is sigma A by epsilon naught. Okay, and so what is the field? The field is E, that is normal, in E perpendicular, which is to the surface, and A. Okay, so a cancels. So because this is 0. Okay, you remember once we had a sigma, only sigma, it was not a conductor, then we had on this, for infinite charge sigma, this was sigma by 2 epsilon naught on this side and sigma by 2 epsilon naught on this side. And now it is 0 here, and hence the same argument, it is E is equal to sigma epsilon naught by n. This is what is also we are getting the potential. Okay, so it is E is equal to 0 inside ensures that charges go to the surface. The charge density gives you an electric field just outside the surface, which is sigma by epsilon naught in a normal direction everywhere, delta V by n. So these are the most important consequences for a conductor. Let's see, how does conductor respond if placed in a field? Okay, That is, if you place a conductor in a field, how does it respond? It will change its charge distribution. Okay, so it and that is called induced charge. And the field could be so it responds by rearranging the surface charge distribution. Why? How? Such that it knows that it has to keep the inside zero. So it immediately solves the electrostatic problem. Okay, nature makes ensures, okay, that it is one of the minimum energy configuration such that you rearrange at the surface the charge density of a conductor such that A inside is zero. And this could be it could be due to external field or another charge nearby. Okay, so the surface charge so developed is, we call it the induced charge on the conductor. uh, Suppose I could take a charge here, then let's say plus q. Okay, then the electric field due to this would affect. Okay, so the electrons will get more attracted towards this, but this whole thing is neutral. So we know then will develop. So there will be some distribution. Okay, and such that there will be uh, some distribution because of the presence of the electric this charge. But it could be just we do not know from where, but this could be an electric field. And I could let's say the electric field, inside this electric field I put a conductor. Okay, then also what it will rearrange as if there was charge as if there was a charge at infinity, for example. So it could be because of either a charge or because of field, but there is a rearrangement of. mm, uh, so what? Suppose E is in this direction, then what will happen? Okay, the charges will similarly would become minus and plus. The actual distribution, of course, depends upon the configuration, but this is what we will call as induced charge. How fast does this occur? An answer we'll have in the second part, but for all our purposes, is almost instantaneous. Okay. For example, is the field, how fast will the field travel inside the body so that the electrons know? But electrons really don't have to move from the body to the uh, from the body to the surface. Okay, they don't have to move from body to the surface. They just rearrange on the surface. Okay, so it is extremely very, very fast. Okay, how fast, we'll have an estimate, but for all our purposes of electrostatics, you can consider that is almost instantaneous. Okay, let's what happens to the fields near the surface of the conductor? Of course, we know that it's normal to the surface. Okay, next I'm saying it's also proportional to the curvature. Okay, curvature of the surface. That is, uh, suppose you give a charge q to a conductor of an arbitrary surface. Let's look at. Okay, so how do you answer the question? What will be the distribution? It's not an easy task. It's a pretty hard task in electrostatics. In fact, most of the equations that you solve is to figure out what will be the distribution. Okay, but some qualitative things we can say. So one thing that we know, that is the potential is the same in the conductor. But what is its value? That needs calculation, okay, and knowing what is happening in the neighborhood, who, which other charge is nearby, which conductor is carrying what voltage. Okay, so that will determine what is the value, what is the equipotential, all the same. So local surface charge, sigma, is proportional to the curvature. Uh, let's, for example, let me just give a qualitative idea. So suppose this is the conductor, and of course E is equal to 0. So you can see that this is a flat surface. So there's uniform okay, and not very, the field intensity is very high where there is a curvature. There is no curvature, this is a flat, okay. Curvature meaning, so this is of very high curvature. So high curvature meaning high field. The electrons tend to crowd around there. So there, of course, sigma would be high. Here, sigma would be low. So again, curvature here. No curvature here, or very less curvature, and so it is uniform, and so on and so forth. This is even more curvature, and hence the so it is normal to the surface. I'm plotting just outside. Of course, beyond that it will be changing, okay, depending on what is there in the environment. But just outside it is normal and is proportional to the curvature. Okay, so qualitatively we can at least say that's much. Just to make that point clear, let me take a very small charge of radius. That's a spherical charge to make the argument clear. And it's charged with radius q r1 and has q1 in it. Okay, and I take very far away. I've taken it very far away such that there is no direct interaction between the two. Okay, and that's why I'm showing it very far away. That is, here it is q2 and r2. Now I make a connection such that they both have the same. Mm, they both have the uh, uh, same potential. Okay, I make a connection. So they have the same potential. Then, of course, what I can say is that is Q1 is by R1 is equal to Q2 R2, and that would say Q1 by Q2 is, and so R1 is less. I already done that. So Q1 by Q2 is less than 1, which means Q1 will have less charge. They're the same potential. One is larger, one is bigger. Then this will have less charge, and this will have more charge. However, okay, we can, so I say that more charge is on the bigger sphere, we just because of the same potential. But I can rework it, okay, and say that all right, this Q1. So Q1 I can write down in terms of surface charge density sigma 1, and Q2 in terms of surface charge sigma 2. So then sigma 1 by sigma 2, okay, here it is now ulta, R2 by R1, and R2 is greater. So sigma 1 is greater than sigma 2. So this has less charge, but it has more charge, surface charge density. Why? Because the R1 is smaller, means the curvature is smaller. Of course, sphere has only one curvature. Okay, in 3 dimension, typically you can have 2 curvatures. Okay, but here the both curvatures are the same, and hence, okay, so this is radius small, meaning curvature is larger, and hence sigma 1 is larger. Just a simple argument to be able to argue that out. Uh, so therefore, we can say that though more charge is on the bigger sphere, sigma is larger for smaller radius, that is higher curvature. Therefore, for equipotential surfaces, sharper the tip or edge, higher is sigma, and hence higher is the field. It's something that we all know, but I wanted to restate it, okay, so that is a part of our, and this is taken advantage of in many, many experiments, many, okay, in the laboratory and modern equipment. For example, to give an example, field ion microscope, where the this is not the magnification can go to millions, okay, or field emission microscope, which use, there are several of them in our campus, takes advantage of this very high field at sharp at sharp tips, okay. uh, So, for example, just to show a sharp tip, this is how it is made with a sharp tungsten or metal. And then on top, in this case, there is a carbon nanotube, which is like something like 10 nanometers width. Okay, so it can be so uh, um, small, the curvature here, that even if a few volts, it can go to uh, thousands of kilovolts. Okay, so carbon nanotubes are being used for tips as a microscopy, almost like 10 nanometer. Okay, uh, so how sharp is the tip for a metal? Okay, so typical metallic tip radius is like 50 nanometer. How do you make that? You just take it and keep etching in a solution. Okay, then it becomes sharper, and it's very easily made. But of course, for commercial thing, you'll have to take a lot of care, but it's very easily done. And the kind of, if you put a few volts, okay, is 50 nanometer, you can get as high field as 10 to the power 9 volts per meter. It's very high field. In fact, this will cause discharge of air. So this has to be used in vacuum. Okay, otherwise, the air molecules in will get ionized, and you will have a discharge. So sharp tip. For example, this is the kind of pictures that you see in a field ion microscope. This is the platinum tip, and you actually see atoms. All the bright spots here are actually atoms. Okay, so this is a field ion microscope image of the end of a sharp platinum. Each bright spot is a platinum atom. In fact, this was the first time done on October 11, 1955. Erwin Muller and his PhD student, an Indian from Simla, okay, Kanwar Bahadur, observed individual tungsten atoms on the surface of a sharply pointed tungsten. Okay, and so these two people, Mueller and Bahadur, were the first persons to observe individual atoms directly. That's around 1955, published in 1956. So just like we have people, Neil Armstrong going to the moon, the first person go to the moon, I think in the history of human civilization, they must have been the first people to actually see atoms. And this is just because of they could make very sharp tip and make a microscope out of that. So qualitatively, at sharp tips, okay, what happens is at sharp tips, you have electrons try to crowd it here, because if they're here, they'll find more electrons per repulsion. Okay, they don't like. Okay, so they avoid. So they try to go to the tip. That's another. This is the qualitative argument that one can give for such behavior. So there are many applications, okay, that these tips are generated. For example, they are used as sharp electrons can escape. Okay, you can actually get electrons out because so high field that even without heating them, normally we heat it to very high temperature so that electrons have enough energy to overcome the work function and come out. But you need not do that. So you can have a cold cathode, that is, you don't heat it, just because the electric field is very high at the sharp tip. Electrons can actually come out of the metal and then become source of free electrons. There are some of the examples of how we take advantage of the fact that field is very high at sharp edges or uh, tips. So let's take an example just to buttress that point even further. That is, uh, we know that dry air breaks down at about 3 into 10 to the power 6 volts per meter. Okay, so giving discharge due to ionization of air. So if you have this much of field in air, you'll start having a discharge. So now I have two balls. One is 10 centimeter, it's a metallic, and a 50 micron metal ball, which I can shape in the workshop. Okay, so now to what voltages can one raise a steel ball of radius 10 centimeter, so without causing discharge? That is, to what voltage I'll raise so that it'll start causing discharge in dry air. Okay, so the field is, for the same field, the argument can be very simple. Okay, so we know that the field goes as r square. Okay, so and this is voltage goes as q by r, and so for the same specified breakdown field which I've mentioned, one can calculate that, see that, okay, that breakdown voltage is proportional to R. Okay, so if it is for 10 centimeter steel ball, okay, then VB would be E multiplied by the radius. Okay, sorry, and that will be 3 into 10 to the power 5 volts, 10 centimeter into that E. Or for, suppose it is 50 microns, which is nothing but 0.05 millimeter, then it is 150 volts, as small as that. So just applying 150 volts will gain the same field. Okay, so that is again making the same point of why sharp points give you very high field. Okay, so because of that, we always in the lab are small speck of dust wherever we are using high voltage, because it gets charged by some means, then it'll start discharging and there'll be lightning kind of. So that is why the we do such a high voltage experiments in an extremely clean room. This is a technical term, clean room, where it is almost dust free. We say that how many particles of what sizes are in the clean room. Okay, and we use our experiments mostly in such clean rooms. And also the high voltage equipment has to be very, very smooth, because if there is small speck of somewhere or roughness, then that it will be very, very high field and it will break down and it can cause severe damage. Okay, so now let's go to caves and cavities in conductors. That's something that we'll deal with. Okay, so now the question is, can a charge hide inside a cavity in a, just like Faraday cage I said, can a charge hide inside the cavity of a conductor? Here is a conductor and a charge is inside. It wants to hide inside that. Okay, so cavity inside a conductor. Suppose there's a charge Q. Okay, let me say that it is charge Q. All right. So we can prove whatever we can prove. So what will happen to that? It will immediately, suppose it is uncharged initially, then it will create. If it is a plus charge, then it will be minus charge here. All right. And what will happen to the surface? Surface will of course get plus charge. Now how it will get distributed depends on the surface, the surface. But the total charge that will be on the surface will of course be plus Q. So though we do not know where the charge is, but the fact that an extra charge is there in the cavity does get communicated to the outside world. But it can be safe if we can put it to ground, and then of course to make it zero, this outside charge will go away, and then of course it can be safe haven for the charge inside the. So how do you prove that there is actually minus charge? So I can always take a Gaussian surface, arbitrary Gaussian surface around it. Okay, and the E is zero everywhere because it's inside the conductor. Okay, and hence in the conductor there cannot be, so it can be, so this is Q, and hence this charge that is appearing at the surface must be minus Q. Any Gaussian surface you take inside of any shape, it is turning out to be zero inside, and hence there must be a surface charge which is minus Q. All right. Now, so in the cavity, the surface, if I integrate, I only know about the integration. I would not know how is this distributed exactly. That will depend upon the geometry of the cavity and things like that. But I would certainly know that minus Q is distributed inside the cavity. So I would not know the distribution sigma r theta phi. It depends upon the geometry and Also how the charges that are inside, how they are placed, what is their distribution. Okay. But if I take a without a charge, a cavity without a charge, but I put a charge on its surface. Okay, it's a cavity, but there's no charge inside. So, cavity with no charge inside, you can put a plus Q on the conductor. Okay, so I can now take a Gaussian surface anywhere. Okay, so what is the potential inside the cavity? Can we check? Of course, it has to be zero. There is no charge. So electric field has to be zero. If the electric field has to be zero, then there is no contribution from the cavity itself. And hence, the it would be at the same potential. So the whole conductor, if there is no charge, must be. So you can make that claim. Okay, if there are no charges inside the cavity, the entire volume of the conductor, including the cavity, is at the same potential. Okay. Um, okay, we'll have several problems dealing with that to make. Okay, let's take an example 3A2. So it's a charge Q is placed asymmetrically. Okay, somewhere in the cavity of a spherical, okay, isolated conductor, okay, with center at O. Now the question is, what is the field outside at a point P, which is shown here? Okay, so it is a spherical surface, and I have its origin. Okay, so origin is here, and then inside the cavity, somewhere asymmetrically I put a Q. Now this is all right. This is not showing it correctly. Um, sorry, in this here it is actually R here. Okay, so that this is a Griffiths R. Okay, so R is equal to R minus R. So will it? The question is, uh, is the field at point P? Is this the Griffiths R? Or what is the? Or is it as if it's at the center? That is this R. It is this R or this R. Obviously, as we just argued, that this will produce minus charges here, and so it will produce plus charges here. And this plus charge, because it's a spherical symmetric, it will be uniform. So it will look like as if plus Q is actually at the center. So this is indeed the field that you would measure. All right. Now the question is whether, how do you know that now the E is 0 here? But the question is the E 0 here? Is it because a combination of this charge, and this charge? Or E is equal to 0 here because of combination of this and this alone? Is it some kind of combination of the surface charge, this and this, such a way that E is equal to 0? The claim can be that it is indeed individually, okay, that these two make sure that E is 0. This again individually make it 0 here. That's why they're saying, okay, how can I say that? For example, okay, the argument can be, well, I can make this radius as large as possible as you want. Same as the Earth's radius, or maybe the known universe. Clearly, that would not have playing a role to make this E is equal to 0. All right, and hence this Q and this minus Q that is at the develops at the induced charge must be in pair, making the E is equal to 0 here. and this separately must be making it E is equal to 0 here. Now that argument must be understood. All right. So how is neutrality achieved? That's what I just discussed. Okay. So neutrality is achieved by the induced charge inside surface and Q separately, and this separately. Okay. And hence this is the correct answer. So it is not sum of all charges, but in pairs. All right. Let's take another example. Simple example. You must have done it. So there is a point charge at the center of a conduction shell. This is a shell now. And this is radius A. This is radius B. So now let's find out sigma E and V for all space, and then the sketch as a function of R. Okay. So let's say first sigma. Sigma could be, what is the sigma at B? Okay, if it is Q, then of course it is spherical cell. So this will be nicely minus here. And that would be, of course, uniform. Okay, so there I can also say sigma A. So sigma A must be minus Q by 4 pi A square. All right. So what would be sigma B? Sigma B, of course, would be minus Q by 4 pi B square. Okay. So because it's neutral, so there would be plus charge all over here appearing. This is something we already know. So sigma B and sigma A, I already know. And what about E? This is, okay, what about electric field? Electric field will clearly appear as if outside. For example, for R greater than B, this will be or 1 by 4, as if or the Q charge is at the center. Okay, so this is of course Q R square R hat for R greater than B. Okay, and for R less than B but greater than A, that's of course the conductor, so that is 0. And for A less than, for R less than A and greater than 0, how much is that? That we can always calculate by a Gaussian surface, a spherical Gaussian surface around that, and that would be simply 1 by 4 pi epsilon naught. Okay, the outside induced charge is not contributing. Okay, so it's clearly the field is going like that, nicely uniformly, and so this will be Q by R square for, again, R less than A. Now what about the potential? What about the potential? I'll let you work that out. Okay, so can you now plot again? So if I plot E as a function of R, of course it goes like that inside till A, then it becomes from A to B it is 0, and then it continues in its decrease path. Okay, so this is A, this is B, and this is the magnitude of E as a function of R. And what will happen to the potential? You can actually work that out, but we can at least sketch the potential. Okay, so this will be like a potential of a Q, but now it will indeed will come down. And what will happen between A and B? Of course, it's a constant. Okay, because there is no. Okay, and what will happen after that? It will continue its journey. Okay, till R is equal to 0. So you can work that. We'll have similar problems in the home assignment. Okay, this is a simple case, but needs to be stated for clarity. Now, the electrostatic force on a charged conductor. The question is, does the conductor feel the pressure? Okay, let's have a conductor, and let's say it's charged. Okay, so there is sigma, and I consider this little piece here, take it out. Okay, so this is, let's say, okay, so this little piece I'm considering what is the force on that. Not take it out, but suppose I take it out, then whatever is rest is there, that will be producing an electric field there. And that field, and this is a charge, so this will also be sigma, let's say, here, whatever. Okay, so now that field, rest of it, would be producing a electric field, and this sigma dA, suppose the small is dA, so dA sigma is dQ. Now this dQ would be filling the force. Okay, and so what is the net field at there? Suppose at that patch, what is the net field? Can we, okay, so the argument is that suppose I take this little patch, okay, which is sigma dA, then very close to it, of course, this would have given me sigma by 2 epsilon naught, and inside this sigma by 2 epsilon naught inside. But when I take this and plug it in here, it has to make sure that inside is 0. All right. So this gets so it'll get cancelled. So that field, then it'll reinforce this field. The field that cancels this would reinforce this field, and hence this field, okay, on this field must be sigma by epsilon naught n. All right. Okay. So that is, so if alone inside when it is plugged in, then of course it is sigma by 2 epsilon naught, its own. Okay. So then the rest of it, what is it contributing here? It is contributing the field. When I take this out, then the what is the field? Field due to rest. Field due to rest of the patch. Okay. That will also be sigma by 2 epsilon naught n. All right. So then what, this is the electric field. What will be the force? Force would be, of course, sigma dA, that is the patch, that is dQ, and electric field is sigma 2 epsilon naught n. So if I take F by dA, which is like force per unit area, then this is sigma square by 2 epsilon naught n. That's the simple argument. Okay, so locally, everywhere there is sigma, okay, it is filling a force which is the rest of the, and I have taken a very symmetric conductor, but isn't it not be? It could be some arbitrary shape, and I could have taken this piece. Okay, so all the because the charges on the surface would still contribute only sigma by 2 epsilon naught at that, and the patch right there, because I'm very close to that, that's like an infinity. Okay, would have sigma by 2 epsilon naught contributing, and total I know is sigma by epsilon naught. Okay, and hence the patch contributing sigma by 2 epsilon naught, and that cannot be giving a force on itself. Okay, and hence the pressure or the force, which is outward force, is this much. I would have written down that. So force on it must be due to the acting on the differential charge. And I've just argued that. Griffiths argues a little bit, saying that, all right, this is that inside it is zero here, inside zero here, and sigma by epsilon naught here, and hence the average force, he says, the average field, okay, where which contributes to the force to that patch, it should be sigma, the average of 0 plus sigma and epsilon naught, and that is sigma by 2 epsilon naught. It's a argument which he makes it, but I think it's easy to understand even otherwise. So the force per unit area, that is small f, okay, is sigma by 2 epsilon naught in the normal direction everywhere. Okay, so it results in an outward pressure tending to push the conductor into the field with pressure P. And we can write down that in terms of the E just outside the surface. Okay, and that would be epsilon by 2 E square. Okay, just from here, that sigma by epsilon naught we could write down as E. Okay, so this pressure is in terms of epsilon by 2 E square. This is an outward pressure, and it is trying to draw the conductor into the field. Okay, and this can be said, this is about every local. It could be for any arbitrary shape also. So what is it that makes working with conductors difficult? Because working with conductors in electrostatics is different in some sense. Why? Because the conductor seems to have a mind of its own. If you can like it to call it called artificial intelligence in some rudimentary form, because it knows exactly what to do to make E is equal to 0. Okay, and so what so far we have done in electrostatic problems is that given the charge distribution, how to find out E and V, or given E and V, okay, find out the charge distribution and so on and so forth. Okay, that's what we had done just before the last lecture. Okay, but now these conductors can rearrange things as environment changes, and that's something. So it is not that charge is fixed in space. Okay, it rearranges on the surfaces of the conductors. So they change their charge distribution, and the charge distribution depends on others, and that in turn changes E and V. Okay, and that can change distribution. So, but things will keep happening till you reach equilibrium in some sense. Therefore, the problem with conductors and conductor problems that we look for equilibrium conditions for charge, potential. Of course, that is true for electrostatics as a whole. This is consistent with electrostatics. That is the problem. So not merely given something and find other things. The arrangement should be such that it should be consistent. Okay, conductors can be charged, neutral. They can exchange charge with batteries or with ground. Okay, so a collection of them doing all those things may appear to be totally intractable problem. Okay, and I'm calling it an intractable madhouse. A collection of charges, a collection of charged conductors in different shapes and lying in different regions in the space. Fortunately, okay, we have some very powerful and reassuring theorems to assist us in our task of finding out what is the final configuration. Okay, if you have charged conductors, some are charged to some potential, some are carrying charge, some are neutral, some are grounded. Okay, so what is the net electrostatic field and potential and distribution of charge distribution? All three has to be answered, and all three have to be consistent with all the electrostatics that we know. All right, so that brings me to something that is familiar. You know that conductors, if we have let's say conductor, some arbitrary conductor Q, so which has a plus Q and is minus Q conductor. Okay, and then we can associate with this arrangement a certain capacitance. What is capacitance? Capacity to store charge. Okay, that is, but this capacity is defined as the charge stored, okay, on the positive conductor, let's say, okay, and then is proportional to the voltage, and this is capacitance, and this is purely geometrical. Okay, this will depend upon the size, shape, distance, orientation, configuration, things like that, but it's purely geometrical. Okay, so this you have done earlier, so I'll go through this quickly. uh, so v so we define q in cv. So capacitance depends purely on geometry, you know already, so I am not going to repeat that. The parallel plate capacitor of area A, thickness D, is simply given by epsilon naught for vacuum. But later in the next, in one chapter later, we will do that. It is can take a dielectric also, epsilon A by D in general. And for example, one could have a concentric metallic cells. Then, of course, 4 pi epsilon naught, 1 AB, the radii A and B. B is the larger one. C is typically positive. But in some situations, we have dealt with negative also. It is a different meaning. For all our cases, we'll say C to be positive. And this B could be infinity. Okay, so then you can talk of one sphere's capacitor. Okay, because B could be some infinity. Then of course it becomes, you can take B common and cancel it out, 1 minus A by B, which is 4 pi epsilon naught A. Simply capacitance is simply proportional to the radius of the sphere, of the conductor sphere. Okay, so and this you can always, I think in high school you have derived this, so I will not derive it, but we'll have to say more about it in a later chapter. Okay, so we'll have a lot more on capacitors in a later chapter. But let me give an advance alert. Though this is C, it looks like is QYV, but in small signal capacitance, which is normally in electronics and all your computers and things like that, we often talk about not this QYV, but small signal. That is, if I place a small voltage dV, how much dQ changes? Or if I change dQ, how much dV changes? Small amount. Okay, could be just in millivolts. Okay, and at a certain frequency. So this is dynamic capacitance, and this is also called differential capacitance. But quite often they one uses this. But of course, the capacitor that you will buy of certain microfarads, electrolytic capacitor, or a paper capacitor, or a ceramic capacitor, those are of course that capacitor. Okay, but in many device applications, we talk about differential, which is dq by dv. With that, I'll come to the summary of this little lecture. Conductors have a mind of their own. No matter what, electrostatically is zero inside. The volume inside the conductor is neutral. Okay, there is no, they do not support any charge because otherwise they will move around, and it's an equipotential. Okay, all charges in a conductor are on the surface. The field just outside a charged conductor should be sigma by epsilon n. A cavity in a conductor hides the details of charge distribution inside, unless of course it is grounded. But the net charge gets communicated to the outside world through exterior surface charge.